Okay, welcome back. We are starting a new chapter today, random variables. So this is our, maybe I should have said chapter 2. It's not a section. Chapter 2, random variables. It's a long chapter. We're going to discuss random variables, what they are, their expectations as integrals, their distributions as measures, and also some related transforms, so-called transforms, some functionals that characterize their behavior, their distributions. So to define what we really mean by a random variable, we're going to start by discussing measurable functions. So our starting point is going to be, again, very basic. So we just start with a measurable space. And later, when we define random variables, we're going to also consider the last part of a probability space, which is the probability measure itself. But for now, we're just dealing with a measurable structure, okay? Namely, just the sigma algebra on a non-empty set. Okay? Our aim in defining random variables is to define some quantities that are interesting for us in the setting of a random experiment. So maybe our probability space, our sample space is very large, and it is typically very large, right? Like a set of sequences, set of functions, etc., etc. But maybe all we are interested in is a simple quantity. Okay? Let me try to give you an example, but our aim is to define quantities that are relevant for a random experiment. Okay, so let me recall this example of coin tossing infinitely many times, okay? So coin tossing forever, where we had this 0, 1 to power natural numbers, meaning the set of sequences of 0, 1s. So every outcome is a sequence such that every component, every member is either 0 or 1, 0 for tails, 1 for heads. And on that space, we define the event that we get heads on the ith toss, so that we can define the following sigma algebra generated by those events, A1, A2, A3, etc., etc., so that we have this basic structure, omega f, defined in a concrete way. Okay, this is an earlier example. So now, in this random experiment, every outcome is a sequence, okay? But maybe we're not really interested in the whole sequence, okay? Maybe a group of people are working on this random experiment, so they are using a common probability space, common measurable space. So everybody needs to define his or her own relevant quantities, okay? So maybe one relevant quantity, let me define it as x. So the number of heads in the first 3 tosses. So what is x? What is capital X? So this is a quantity that is random because the total number of heads in the first 3 tosses depends really on what particular outcome we observe as the result of the experiment. Therefore, the only way to define it concretely is to say what value it takes for every possible omega. So this is x of this omega 1, omega 2, etc., etc. And how do I define this in terms of the sequence? Can you define it as a function? How can you count the number of heads in the first 3 tosses? So what are those values? Omega 1, omega 2? Just zeros and ones, right? 0 for tails, 1 for heads. So how would you count the number of heads in the first 3 tosses? Would you look at omega 4, for instance? We're not interested in that, right? So we're interested in omega 1, omega 2, omega 3, and x of omega is what? In terms of omega 1, omega 2, and omega 3, how would you define it? Just the sum of 3 things, right? So let's define it as omega 1, omega 2, omega 3. That's it. So tell me the outcome. I tell you what the number of heads in the first 3 tosses is. What are the possible values of x? What are the possible values of x?
0, 1, 2, 3.
Exactly. So x can take one of the values in 0, 1, 2, 3. So x is indeed a function from omega to the set 0, 1, 2, 3. Since it is a function, it takes only one of those 4 values, okay? And for sure, it's going to take one of those values. So if you look at the outcomes for which we have x of omega equals 0, what is this? So we're going to write it in a special way in probability theory, which is x equals 0. And this is what we mean by this. If you're more familiar with the notation in usual set theory and functions, maybe in your calculus courses, this is the preimage of the set 0 under the function x. It's not the inverse function. It's the preimage, right? It's a set of all outcomes in the sample space for which x takes the value 0. Okay? So this means what? We want all omegas for which omega 1, omega 2, omega 3 are all 0. Right? No heads at all in the first 3 tosses. This means what? We should have tails, 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 and the rest we're not interested in. So can we write it in terms of A1, A2, A3? A1 is the event that we get heads in the first toss. A2 is the event that we get heads in the second toss, and so on. Can you write it as unions, intersections of A1, A2, A3?
Intersection of complement of A1.
Exactly. So A1 complement means it's tails on the first toss, and tails on the second toss, and tails on the third toss. So what can you say about this event? What kind of a set is this? So whenever you have a subset of omega, what do you look at? The sigma algebra. Is this in the sigma algebra that we define here? Is this event in F? Yes. Why? Because A1 is in this sigma algebra. Its complement is in the sigma algebra. These 2 complements are also in the sigma algebra. Their intersection as a finite intersection is also in the sigma algebra. So we know that this is in F. You can write down the others. So for instance, x equals 1. What does that mean? Just 1 heads. just one heads. So this means you can get it in the first one, but not in the second, not in the third. Or you can get in the second one, so not in the first, not in the third. Or you can get this in the third one, not in the first, not in the second, but in the third. So this is, again, just set operations finitely many times. So this is also enough. Let's write down x equals 2. So this means we need 2 heads, but no 1 tails. So maybe A1 and A2, but not in A3. A1 and A3, but not in A2. Not in A1, but in A2 and A3. This is also enough. And finally, we have x equals 3, which means we have heads, heads, and heads, which is also enough. Let me say here that we give this event a name. So this is the event that x takes the value 0. So this is the event that x takes the value 2, etc., etc. So if you look at x, so the function x is completely determined by the events x equals I, where I is 0, 1, 2, or 3. Since each of these events is f measurable, we will say that x is an f measurable function. So we're interested in a function, but this function is nothing but an economical way to represent a bunch of events. X equals 0, x equals 1, x equals 2, x equals 3. So if all those 4 events are in your sigma algebra, then what you say is that your function is also in the sigma algebra, meaning that it's measurable with respect to this sigma algebra. Okay? So that's the definition of a random variable. That's the definition of a random variable. We're going to generalize it now. Let's make a more general definition. So let's fix 2 measurable spaces. Omega f and E script E. So E script E is the state space. So E will be 0, 1, 2, 3, for instance. Okay? And script E will be, for instance, the power set of this set. Okay? So this is the sample space. This is the image space. Okay? So we're going to define a function from omega to E. So here's the definition. A function x from omega to E is said to be a random variable or a measurable function with respect to f and script E, the sigma algebras, if the preimage of every set in the sigma algebra script E is an interesting event for us, is in the sigma algebra on the sample space for every D in E. So here's a related picture. So here's what we mean by measurability. Okay. So we have omega E. So for instance, E is just the real line, or 0, 1, 2, 3. Okay. So since this is typically a set of numbers, or maybe sometimes a subset of Rn, for instance. So typically this is going to be a numerical type of space, okay? So there's going to be a sigma algebra, a natural sigma algebra here. If you work with the real line, it's going to be which sigma algebra? Borel, right? So there's going to be natural sigma algebra there. So your function omega, x, is doing the following. It takes omega and maps it into a value in this set. So this is your sample space, and this is your image space, or sometimes state space. So what we mean by measurability is that, hey, we're interested in a quantity, okay? So we are interested in events about this x. For instance, x is between 1 and 3. That's an event. That's a range of values. So let's call it D, okay? For instance, D is 1 to 3, an interval. And this is our function x. What we want is that events of the form x takes values in D make sense for the random experiment. Meaning that if you go back to your original space, if you look at this x inverse D, or the event that x takes values in D, we want this to be an interesting event for us. Measurable, or interesting event. In our example, it was the check that x equals 0 is an F, x equals 1 is an F, and so on.
So in the finite cases, checking each singleton is enough.
We're gonna get to that point. Simplifications will be possible, okay? Let me also introduce some notation, maybe. Things like this. So we're talking about random variables or measurable functions, okay? Just the same term, okay? It's just the same term. If you're in the probabilistic setting, you call it a random variable, but you can also use the term measurable function. Exactly the same, okay? So they are defined with respect to the sigma algebras on the two spaces that we're working with, okay? So for this reason, we denote by L0, okay, of omega f and E script E, okay? And sometimes, if you know what the sigma algebras are, just omega and E. And sometimes just E, if you know what your omega is, if there is no confusion about your omega, okay? So you can use any of those notations as to denote the set of all random variables with respect to f and script E. And when E is the real line, so L0R is just denoted as L0. So when you just write L0, it is the set of real valued random variables. When you write E equals R bar, so this is going to be just R bar here, we're going to call them numerical random variables. Numerical. Set of all numerical random variables. For instance, the x in our example is a numerical random variable because its values are numbers, right? Is there any case where we are interested in non-numerical random variables? Well, why not? Why not? Let's give an example. So, not all random variables have to be numerical. For instance, in the previous example, the coin tossing example, define y of omega as omega 1, omega 2, omega 3 for every omega. What does that mean? So in the previous example, you were interested in the total number of heads in the first 3 tosses. Now you're interested in something more than that. You want to know if you get heads in the first toss, in the second toss, and in the third toss. The whole information about the first 3 tosses. Okay? This is what you want. This is something that you cannot capture if you just use x, because x is just telling you the total number of heads, not the order that you received them. If you're also interested in the order of receiving heads and tails in the first 3 tosses, then you should perhaps keep all 3 parts of this outcome. So that's a function. Y is a function from omega, which was 0, 1 to n, set of sequences of 0, 1s, into 0, 1 to 3. 0, 1 to 3. Right? 0, 1 here, 0, 1 here, 0, 1 here. And this is not a numerical set. It's not a subset of the real line or extended real line. It's a Cartesian product of 3 spaces. So this is also, this can also be a random variable. Okay? So, okay. Any questions so far? So now we introduced this notion, but we should somehow convince ourselves that this is a convenient notion. We can work with that. We can do calculations with that. For instance, if you have 2 measurable functions, 2 random variables, okay, from a first space to a second space, and another random variable from the second space to a third space. What if you look at the composition of the 2 functions? The composition, which is a function from the first space to the third space. Is this again a random variable? So if the answer is yes, then this would be something nice, something convenient, right? So our aim is to prove properties that make measurability not too difficult for us. And here's the first of such properties. So we have 3 measurable spaces now. So let me keep the same notation for the first 2. And the last one, g script g, okay? And you have functions from omega to E and E to G that are measurable. I'm not going to say with respect to which sigma algebras, because we only have one sigma algebra for each space. So X measurable means X is measurable with respect to F and E, and Y is measurable means it's measurable with respect to script E and script G. Okay? So we have only one sigma algebra for each space. Now, define their composition Y composition X by this formula, Y applied to X of omega. So Y of Y composition X is a function from omega to G, is measurable. So let me say, then Y composition X is measurable. Let me draw a picture so we know what we're talking about. So omega, E, and G. So here's what is happening. You have omega, okay? Using X, you map it to X of omega. And using Y, you take it as a point in the domain of Y and map it to Y of X of omega. So at the end of the day, you get your composition, which takes omega to Y of X of omega. So let's show it's measurable. Proof. So what are we going to show? Y of X is a function from omega to G. So we need to take a set in the script G and show the event that Y of X takes values in A is in F. This is the task. So we're taking a set here. Okay, and see how we can trace it back to omega. Okay, so let's write this event. Y composition X is in A means the set of all omegas for which Y of X of omega is in A. Okay, so Y of something is in A means what? This something is in the pre-image of A under Y. So I can rewrite it as X of omega is in Y inverse of A. Not inverse, but pre-image of A under Y. So here's where we are. So we're getting back to this space. So this is Y inverse A. We want X of omega to be in Y inverse A. So now let's do it again. X of something is in a set means what? This something, which is omega, is in X inverse pre-image of whatever set we have here. Therefore, this is nothing but X inverse composition Y pre-image of A. X pre-image Y pre-image of A. Or let me even write it this way, okay? Pre-image of A. So now we have to argue that this is an F. This is an F. So we have to use the measurability of y and x. So A is in G. Y is measurable from E to G. From E to G. This means this is in where? Script E, right? This is in script E, since A is in script G. And one more step taken back. So this is going to be x inverse of y inverse of A. And since this is in E, this must be in F, because x is measurable. So this is because x is measurable. This is because y is measurable. And that's the end of the proof. So this is already means y composition of x, the preimage of A under this composition function. All we did is to see that the order is reversed when you look at preimages, okay? Which you can also know from just theory of functions, okay? But I like to describe it this way through images, which looks very intuitive and nice. Okay, that's a nice property, but still it's not like a very computational tool. Still, we have some issues with measurability. Still, measurability looks very difficult. Why? So here's some complaint. Measurability of a function, of course, looks difficult to check. We must ensure x is in D in F for every D in script E, which is a huge sigma algebra, for instance, the Borel sigma algebra. Can we reduce it down to a smaller collection of sets in script E? For instance, would it be enough to check this condition not for every set in the Borel sigma algebra, but maybe just for intervals? So this is going to be the next question that we're going to answer. And luckily, the answer will be yes, so that we will need to make less number of checks. So here's the proposition. So, okay. Again, we have omega f and E script E, okay? So let P, script P, be a collection of subsets of E that generates script E, meaning that the sigma algebra generated by script P is script E. So now x omega to E is measurable with respect to F and E, script E, if and only if x in D is a measurable set for every D in now P. Okay. So these are very similar statements, right? So the first one is saying this event is an F for every D in script E. This is saying X is in D is an F for every D in script P. So the only difference is between the places where we look at for those sets, D. Okay? So let's do the proof, okay? First of all, this part is clear. Let's explain why. Well, if, let me say it this way. So since P is already a subset of E, script E, we have this part automatically, without effort. There is nothing to prove, because we're already assuming that this is an F for every D in script E, which already includes script P. Let's do the other part. Is this part clear, by the way? So just look at the definition of measurability. All we're saying here is that X is in D is in F for every D in script E. Okay? This is what we're writing here. Okay, let's do the other part. Suppose X is in D is an interesting event for every D in P. Show X is in D is in F for every D which is in E, which is sigma of P. So how would you proceed? How would you proceed? You want to show a property which holds for every set in this collection script P. Okay? You want to extend this property to the whole sigma algebra generated by script P. So what is the trick? What is the idea that we used last time when dealing with monotone class theorem? Anybody remembering? So you have a property, and you want to extend it. How would you do that? Any ideas? You want to extend this property. So without thinking anything, just look at the collection of all sets that satisfy this property, right? Let's just define a collection like that. So the idea is this. Let's just define the set of all these for which this is true. And we know script P is a subset of script A. This is what we assume. Can we conclude sigma P is in A? Okay, let me wait. So P is in A. How would you pass to the conclusion that sigma P is in A? What would you need to show? A is a sigma algebra, right? This would be enough, because this is already the smallest sigma algebra containing P, and this is a sigma algebra containing P. So enough to show A is a sigma algebra. And of course, I will leave it as an exercise, because you know what to do, right? Just go to the definition of sigma algebra and check every property one by one. Okay. So it's important to digest this proof. There is something going on here. Well, let me say it this way. There is not much going on here. There is not much going on here because we did not use monotone class theorem. So remember, monotone class theorem is like a magical tool that we apply whenever we have a pi system, right? If the script P were a pi system, then we would have tried showing this is a Dynkin system so that by monotone class theorem we can say the sigma algebra generated by this pi system is also in A. So this proof is not that difficult. in the sense that it does not require the use of monotone class theorem. Let me put it as a remark. This proof does not use the monotone class theorem. Indeed, we did not even assume script P is a pi system. We did something much simpler. And this was the following. P is in A implies sigma P is in A whenever A is a sigma algebra. And P is anything, any collection of subsets. Okay? That's the end of remark. And maybe we should add a corollary for numerical random variables. So let's just apply it to the case where E is the real line or the extended real line. Doesn't matter. Okay? So let's try to illustrate how useful this result is, okay? In a special case, in a very common case, where we have numerical random variables. Most of the time, especially in the first part of the course, we're going to deal with numerical random variables. So all those random variables that you know from your undergraduate courses, Gaussian, uniform, all discrete ones, Poisson, etc., they are all numerical, right? And the non-numerical ones are going to appear in the second half, and they're going to be random vectors, okay? Random vectors. So we're going to deal with random vectors mostly in the second half of the semester. So let me put this corollary here. So suppose script E is this extended real line. So we have a function from omega to r bar. So the restatement of this proposition is the following. X is a numerical random variable, namely measurable with respect to f and the Borel on r bar, if and only if x is less than b is an event for every b. For every b. So you don't look at an arbitrary type of set here, but instead you restrict yourselves to the events of the following form. X is taking values in an interval. So recall that the Borel sigma algebra on the extended real line is generated by intervals of this form. It was by definition, I guess, right? And just call it script P. It's a pi system, but we don't even need that to be able to use the proposition. We don't even need that. So x is in minus infinity to b is something that we just write this way in short. And just apply the previous proposition. It's a straight application. You can even have more such characterizations by considering other collections generating this Borel sigma algebra. We can make a longer list. For instance, x is a random variable if and only if, let me first repeat what we just said, for every b, if and only if x greater b is an f, for every b, or x is between a and b is an f for every a less than b, etc., etc. Just take any collection that generates the Borel-Sigma algebra, and it is enough to check that events of x is in that kind of an interval, okay, is a measurable set. Let me write it this way. X is in I in F for every interval I. Because intervals, open ones, half open, half closed ones, all types of intervals, they all generate the Borel-Sigma algebra generated on the real line. Okay. Any questions so far? So now at least we got something practical, right? You want to check some random variable, some usual type, numerical random variable is measurable. You want to make sure it's measurable with respect to a sigma algebra. All you have to do is to check x less than b is measurable, or x greater than b is measurable. So don't try to work with a crazy Borel set, right? You don't need to work with all those crazy Borel sets. Just look at simple things like intervals of this form, or of this form, or of any form you want. Okay? So let's give a break and meet in 10 minutes, okay?